In this lecture, I'm going to show you how to actually add the equatorial and axial substituents to the chair structure. Okay, so we have a chair structure, and each carbon has axial and equatorial groups. So let's start by drawing the axial groups. They're the easier ones to draw. So we want to be able to add 6 of them to 2 separate versions of the chair structure, or 2 conformational isomers, or a chair and then a flipped chair version. So I'm going to start by drawing the 2 chair structures. Okay, drew them quickly because we're good at this now, right? Okay. Just to start, I'll draw dots at the 6 carbons. And then what we want to do is we're going to add straight lines to each of the carbons, and it's going to alternate up. If you look, that looks like it's more up than down. Up, down, up, down, up, down. Now this back one is tricky. This back one, we show a line break because this lower line within the ring is actually, that bond is in front, and so it's as if it's cutting off the bond that's in back. If we had just drawn it as a full straight line, whoop, goodness, excuse me, it would be hard to tell that that bond was in back. So just by cutting this last bond in half, it's a little reminder to us that that bond is actually in back. Okay, so we have to do the same thing over here, except now we've done a chair flip. And so if we look, the furthest left carbon, which was up, is now going to be axial down, then up, then down, then up, then down. Now this is the carbon that we cut in half, or excuse me, that's the bond that we cut in half, axial pointed down behind the front line. Okay, I'll kind of match up these groups. So the relationship between these two, and I'm going to start drawing equilibrium arrows, is a chair flip. 2 half-headed arrows pointing in opposite directions suggest that these two interconvert by a process called equilibrium. And that's a chemical process we'll look at in future lectures, but anyway, I do want to start invoking those arrows. So what we need to be able to do is you need to be able to identify whether the group, and it should be the axial group, let me clarify, should be up or down. Okay, should be up or down. So my trick, and I'm sure there are multiple tricks, just do what works best for you. The important thing is that you're able to just draw accurately the axial positions, the axial bonds on a chair structure. So what I do, just my tip, is I find the quote arrowhead, I guess, at each atom, and that arrowhead determines the direction the axial group points. Okay, so what am I saying? Well, again, this is just like a little trick that I have, so you have to practice to get good at using this trick. It can be helpful though. So I'm gonna draw a bigger chair structure, and then what I'm saying is that we start at an atom. So an atom is a corner, and we draw an arrowhead. If you look, the way that the corners of the chair structure kind of, maybe I'll use a different color, kind of come together. They come together at a point that looks like it could be the tip of an arrow. And so each corner has an arrow. Some arrowheads are narrow, and some are wider. Some of the corners have the arrowheads on the inside of the ring, which are the 4 that I've got drawn so far. Some are on the outside of the ring, which are these 2. So all of these arrowheads are pointing in some mostly diagonal direction. But what hopefully you can be able to do is look at each arrowhead and identify the ones that are up from the ones that are down. Like the two that I'm labeling down, hopefully you can see that based on how I drew the tail, if you had to say that arrow's either up or down, hopefully you can say that for both of those, they're down. So we have up, down, and it alternates up, down, up, down, up, down. So if you can't see one arrowhead, like maybe it's hard to see, you could just go to the position next door. Maybe it's a little bit easier to identify whether that arrowhead's up or down, and that'll tell you whether the axial position, where that axial position that you're struggling with is pointing, because it's always alternates from up to down. Okay, so we could do the same thing on the opposite chair structure. I'll work through this one much more quickly. Hopefully you are starting to get the idea. So there's an arrowhead down. There's two that are up. There's two that are down. So the corners again define arrowheads, which then determine whether we're up or down. And because we're doing a chair flip, the relative positions don't change, but whether or not the axial position points up or down flips. So that's kind of why we stick with this term chair flipping, to show the interconversion between the two. We use that term chair flipping instead of free rotation or conformational isomerism, because chair flipping reminds us that so many things about these two structures flip as we go from one side to the other. So those are the axial positions on the ring. Let's move on to the equatorial positions. And did I actually, oh, I guess I drew it twice. I probably don't need to. Well, I could. I'm gonna go back and do this. I'm gonna go ahead and with the black pen, just draw these positions. I guess it didn't make the drawing look, oh, that one's gonna look bad. Okay. The break. I mean, it matches the structures up above, but at least I added the groups. Okay, so drawing the equatorial positions now, or I should say groups, the equatorial groups attached to each position. So the things we have to recognize is they're slanted horizontally. Okay, that's one thing. They're slanted horizontally. And by slanted, that means there's kind of this left direction and a left-right direction, and then there's an up or down direction, right? That's how you get a slant or a diagonal, is you have both an up-down component, a horizontal and a vertical. Yes, let me get that right, horizontal, vertical. So you have both of those components in these structures. And there's a little bit of a trick to help you identify the horizontal and vertical components. So they're slant horizontally. What that means is that we have a horizontal and vertical component. If you've taken any math courses that involve vectors or arrows, hopefully that kind of makes sense. There's an X and Y component to both of these if they're not perfectly vertical, as is the case with axial positions. Okay, so how do it's kind of useful to see whether it's pointing left, right, and up, down. So in terms of the vertical component, it is opposite. I guess I don't need to put that in parentheses. The vertical component is always opposite of the axial group. So once you know what the axial group is, and we have those little arrowheads, it's going to be pointed in the opposite direction of the axial group. That is, if the axial group is pointing straight down, we're not going to have an equatorial group that's down and to the left or down and to the right. So that's the vertical component. Now the horizontal component of our diagonal equatorial group, there's a slick trick that a student taught me my first year to see this, as opposed to just brute force memorizing, which is what I recommended. But the 3 carbons on the left half of the chair have left pointing equatorial groups. And vice versa, but let's break it down. What I'm going to do is draw like, I don't know, I'm just going to draw the axial positions for each of the 3 carbons. Now what I'm doing is I'm cutting this chair structure in half. So there are 1, 2, 3 carbons on the left side and 1, 2, 3 carbons on the right side. So this is my left side. So again, we've got 3 carbons on the left side, 3 carbons on the right side. So 2 of the axial groups are pointing down and 1 is pointing up. What this tells us is that if we start here, if we look at this position, my horizontal component for all 3 of these equatorial groups will be left. And my vertical component of this slant will be down because the axial group is facing down. So I'm just going to draw a slant this way. Now over here, and similarly over here, we're going to have slants that are pointing upwards because our axial groups are down. We're always opposite of the axial groups. So we're going to be up and to the left, up and to the left, up and to the left. Okay, so the black is what we want to pay attention to. Okay, now let's do the and vice versa. That is, the opposite's true of the right-handed structures. The right-handed, the right 3 carbons in the ring have right pointing equatorial groups. I think this is a really helpful way to, and this is, props to this student. This is a really helpful way to think about this. If I'm going to give names, it was Courtney, by the way, so in case this shows up on YouTube and a student's like, hey, that was me. Okay, so I'm going to cut this in half. I think this is really helpful. I interrupted myself. I think this is really helpful because when we do chair flips or we kind of reorient chairs, let them roll around in space, these rules still apply as opposed to brute force memorizing. We would then have to know every little way that a chair structure could be drawn. Like I like to draw them parallel to the bottom of the paper, so they're kind of always going in left to right, or horizontally rotated. But if you move them 90 degrees, it's still a chair structure and it still counts. And these rules luckily still apply. So I have my 3 carbons that are on the right side of the chair structure. I'm going to go ahead and draw the axial positions, which are pointing straight up for 2 and then down for 1. Again, the opposite of the axial groups on the other side. Okay, and then what I can do is add the equatorial positions, which if this one all the way, my pen is all the way to the right, if this one all the way to the right has a downward facing axial group, but it's on the right side of the chair structure, then it's going to be pointing, the equatorial group is going to be pointing up and to the right. I'm going to go to this carbon, and its axial group is pointing up, so the equatorial position is going to be pointing down and to the right. And then this carbon over here, we're going to see down and to the right once again. So we have a little mnemonic to help us remember whether our equatorial group is pointing up or down, and then left or right. Those are the 2 components for a slanted line, and that's what you need to be able to figure out where you draw your equatorial positions. Now, you might say, well, what if I get it wrong? What if I had drawn that last line like this? Well, you didn't depict a chair structure correctly. Remember, these are accurate depictions of 3-dimensional molecules in the universe, 3-dimensional molecules that happen to be of the most important ring system in the universe. So it's important to look at this stuff. There's another point that I want to make about equatorial groups, and equatorial groups are parallel to the bonds in the ring. So not only are they down and to the left, down and to the right, that sort of thing, but they're parallel to the bonds within the ring. And it's the bonds that are 2 bonds away. Okay, it's a little cumbersome. You could actually just use this rule if you fully understood it to help you draw the equatorial groups, but I think it's kind of a confusing rule to articulate. I'd welcome any feedback, but what I'm saying is, let's do this. Let's go ahead and draw a chair structure, and we're going to add the equatorial groups at each position. I've done this a while, so I can draw them kind of fast. What I'm saying is that if we look at any one equatorial position, that line that I've drawn down and to the left in this case, or up and to the right, kind of works across the ring. Those 2 lines are going to be parallel to bonds within the ring, and it's going to be this bond and this bond. So 2 lines away. What I'm saying is you start here with a star, you skip 1 bond, and you get to another line. So every equatorial group is parallel to bonds inside the rings that are 2 lines away. Let's change the color and look at a different bond. So if we go here, what I'm saying is that we would skip what I've already drawn with an X. We'd skip that X and go into the green. Now we could go in either direction, as I kind of hinted towards. In this second case, we'd skip the star. And then that's parallel to, again, 2 bonds away, the other equatorial group that's hanging off the ring. And then hopefully you can see that these last 2 groups are parallel to the last 2 lines. So we have 6 equatorial groups. Each equatorial position is parallel to another equatorial position and 2 bonds inside the ring. Okay, so that's some guidance on, and again, all of this is designed because this is what makes these rings so special. And we'll look at more details chemically as to why this is, but following these little rules means that we accurately depict these things. And these little mnemonics I have of left side tells you if it's pointing down and to the left or down to the right, right side, that sort of thing, and then up and down relative to the axial position. What's nice about these rules is, again, it applies to every chair structure. So we did the same thing and we considered the equatorial positions at this chair flipped ring. What we would first do is perhaps cut this in half. Cut this in half when we have a left and a right. And then I like to start at the corners. It's a good place to start. Either corner, or sorry, furthest left or furthest right corner, excuse me. What I could do is, now that I've mastered my axial positions, so I can add them quickly just so I can see. Now, the other things to think about too are axial and equatorial. Excuse me, equatorial, like axial, alternates whether it's pointing more so up or more so down. It's just not perfectly up or down. Okay, so I'm going to start at the dot. Now its axial position is pointing up, so its equatorial position must be pointing down and to the right because it is on the right side of my molecule. I did my best. It's unlikely it'll ever be perfect, but that bond is parallel to the other 2 lines inside the ring, and it would be parallel to the carbon across the ring. Sorry, I don't mean to scrunch that into my other chair structure, but I guess they're giving each other a high five. But now the yellow bonds are all parallel to each other. Okay, I can do the same thing for this position. So that position is on the right side of the molecule. We're going to be pointing to the right, and we're going to be pointing up because the axial position is pointing down. I drew a line that, to the best of my ability, was parallel to this line and this line. Some of those corners are a little bit difficult. I get it. Okay, and I have one more position on the right side of my ring. It's going to be pointing up and to the right, and it's going to be parallel to the last remaining bonds inside my ring, these two bonds. Okay, so pointing up and to the right this way. Let's go over here. Now we're going to be pointing down and to the left because our axial group's pointing up and we're on the left side of the molecule. We're going to be parallel again to the purple lines. So purple there. And then to our last position, we're going down and to the left, and we're going to be parallel to green. So those are the most colorful chair structures I've ever drawn in my career, because usually I just come with a pen. You all have lucked out. But just in case you didn't find yourselves lucky to see all those colors, I'm going to redraw the axial positions for both depictions of my chair structure, both conformational isomers of my chair structures without any colors. So we're pointing this way. There. 6 equatorial positions for each of the chair structures. If you can identify the axial and the equatorial positions, you are in really good shape. The reason why is because we have this ultimate goal that we want to do, where we want to convert a flat structure into a chair structure, okay? So the goal, really, a very important goal, worth a lot of points on exam 3, is going to be draw a chair structure from a, quote, flat depiction. Okay, so let's say I just, for example, took this molecule where I put a methyl group, which is a CH3 hanging off of a main chain, and an OH group, which defines this molecule to be an alcohol. If you've seen the functional groups part of the lab this week, excuse me, the IR lab, which I guess is this week as of recording, last week, whatever. Okay, you get it. So, so I've got these just two things hanging off of my 6-membered ring. And so what I want to do is draw a chair structure. So when my task, and it'll be your task eventually, is to draw a chair structure, I really have a lot of options ahead of me. So I'm just going to draw the chair structure that I'm most comfortable with. If you picked a chair structure where your left flap was, instead of up, it was down, and your right flap was up, as long as it was a chair structure, you're good, okay? It's just, there's a lot of answers, a lot of possible answers. Okay, now what I want to recognize is that I've got an OH and a CH3 attached to 2 carbons on my ring. And so the other thing I get to do is I get to pick which carbon, in this case, I want to be the square and which carbon I want to be the circle. I just get to choose, okay? As long as they have the relative, they are in the same distance away from each other in both depictions. They're, if you look, we could kind of trace around, the square is 1, 2 carbons away from the circle. So my favorite place to add molecules is on the furthest left or furthest right. So if I pick this furthest left carbon to be the square, then I have to make sure that I'm 1, 2 carbons away from the circle. Okay, and no matter kind of how you count this, the circle is 2 carbons away, so whether we went on the left side or the right side. Okay, once we've made the proper selections, and again, I could have picked any 2 carbons as long as they're the appropriate distance away. For example, whoop, I don't want to lose that. For example, if I had picked this to be the square and this to be the circle, that would have also been fine because they're 2 carbons separated. Those are just sometimes more awkward positions in my opinion. I really like the positions on the side just because I'm more comfortable drawing the axial and the equatorial. Then what I get to do is, maybe I say this is an axial position. I'm going to add an OH. This is an equatorial position this way. I'm going to add the CH3. And I'm done. I get all the credit. I'll have more tips on this. I went through this quickly. I just wanted to show you what the goal was. We want to get to this point. You know, there's some other tips I want to provide. Like for example, after you select the carbons and assume that they're in the, and show that they're the appropriate distance from each other, you then want to draw both groups, whether it's axial and equatorial. And then we're going to run into situations where it's important to properly select one that is the axial position over the equatorial position. So there'll be instances where we need to know those sort of things. But this was a good kickstart molecule. So again, that's the goal. What should be your goal right now is continuing to get better and better at drawing chair structures, and in particular, practicing drawing the axial and the equatorial groups attached to the chair structures.